Alright, March 15th through the 19th, we're going to be looking at lesson 21. Alright, lesson 21 is special relationships within right triangles, dividing into two similar subtriangles. Alright, so it says, use the diagram below to complete parts A through C. Are the triangles shown above similar? Alright, so in order for the triangles to be similar, I would have to prove them to have parts that were congruent. Alright? So let's look at what they give us. We know that both triangles have a 90-degree angle. It tells me that this angle is 33 7/10 and this angle is 56 3/10. Alright? So if I add, let's just figure out what this angle is. So 90 plus 56 3/10 would be 146 3/10. And if I subtract that from 180, I get 33 7/10. Alright, so the measure of angle C is 33 7/10. So if you see, all three angles of this triangle are equal. Alright? So I can say yes that the triangles are similar by the angle-angle criterion. Not equal, they're similar. They are not equal because if you will notice the sides are not the same length. So the triangles are similar by the angle-angle criterion. And what that means is that angle A is equal to the measure of angle X. That measure of angle C is equal to the measure of angle Z. And that the measure of angle B is equal to the measure of angle Y. Now I didn't do this over here, but guys, if this is 90 and this is 33 7/10, then I would know that this is 56 3/10. Alright? So they are similar triangles. Determine the unknown lengths of the triangles. Alright? So it wants to know the unknown lengths. So I know the lengths of two sides of this one. So I've got to figure out this one. I don't know the lengths of this side or this side of the triangle. So we will figure that out. Alright, so we're going to start with YZ. We're going to let X equal represent, we'll use the word represent, the length of YZ. Alright, so because the triangles are similar, I can set up a proportion. So I can set up a proportion from this triangle to this triangle. So I'm going to set it up as 3 over 2 is equal to, this side matches side 3, so X over 1.5. Alright? And then I can cross multiply for proportions. So 2 times X is 2X. And 3 times 1.5 would be 4.5. Alright? Divide by 2. So X is going to equal, if I do 4.5 divided by 2, I get 2.25. So I know the length of Y, or of ZY, is 2 25 hundredths. Alright? Alright, so then let's look at, now I can look at AC. Alright? We'll let Y represent AC. Now, if you know this is a right triangle, So therefore, I can say that AC is the hypotenuse. And so therefore, I can use what we call the Pythagorean theorem. Alright? In a right triangle, I can use what we call the Pythagorean theorem. So the Pythagorean theorem is set up like this. A squared plus B squared is equal to C squared. C being the hypotenuse, and A and B being the legs. So I can go, okay, 2 squared plus 3 squared is equal to C squared. So I have 4 plus 9 is equal to C squared. 9 plus 4 is 13 is equal to C squared. And I would take the square root. So C is equal to the square root of 13. Alright? Alright, so I know the length of this is the square root of 13. Alright, so the other side that we have, we need to figure out the hypotenuse of my other triangle. Alright, so we'll let Z be the length of XZ. Alright. It's a hypotenuse, so I can do the same thing. So I've got 1.5 squared plus 2.25 squared is equal to, and instead of C, I'm going to use Z squared, just because we said we're going to let that equal Z. Alright, so we're going to get our calculator. 1.5 times 1.5 is 2.25 plus 2.25 times 2.25 is 5.0625. Alright, so we'll add those together and we get 7.3125. We're going to take the square root of that. So Z is equal to, and guys, if I take the square root, you notice it's not a perfect square. So I'm just going to say it's the square root of 7.3125. Okay? Alright, let's look at C. Explain how you found the lengths in part A. Well, since the triangles are similar, then I can use the values of the ratio of corresponding sides to determine the length. Alright? So since the triangles are similar, I use the proportion to find YZ. I use the Pythagorean theorem. For the length of AC and XZ. Alright, sorry guys. Alright. Recall that an altitude of a triangle is a perpendicular line segment from the vertex to the line determined by the opposite side. In triangle ABC below, BD is the altitude from vertex B to the line containing AC. Alright? So, BD is my altitude. How many triangles do you see in the figure? Well, you should see 3 triangles. Alright? There are 3 triangles here. The whole triangle, this triangle, and then this triangle. So there are 3 triangles in the figure. Alright? Identify the 3 triangles by name. Note that there are many ways to name the 3 triangles, Ensure that the names students give show corresponding angles. Alright, so I need to make sure my angles are all matching. In other words, I've got a right angle here, I've got a right angle here, and I've got a right angle here. So I need to make sure my right angles are matching up. Alright, so I have triangle A, B, C. Alright, that's my whole triangle. Let's go to this triangle right here, this triangle with the A, the D, and the B in it. Alright? So, triangle A, my right angle is D, B. And then I'm going to go to this triangle here, and that has D as my right angle, so D is going to be in the middle. So I have triangle B, D, C. We want to consider the altitude of a right triangle from the right angle to the hypotenuse. The altitude of a right triangle splits the triangle into two right triangles, each of which share a common acute angle with the original triangle. In triangle ABC, the altitude BD divides the right triangle into two subtriangles, triangle BDC and triangle ADB. So it wants to know, is triangle ABC, and this right here means similar. So is triangle ABC similar to triangle BDC, and is triangle ABC similar to triangle ADB? Alright, so we've got to figure this out. Alright, so we want to start with triangle ABC, the whole triangle, and triangle BDC. Alright, so we know that there are 90-degree angles. Alright? But I also can look at this. In the name of my triangles, it tells me that I share another angle, C. Because they share this angle, that means it is congruent to each other. So, triangles ABC and triangle BDC are similar by the angle-angle criterion. Alright, because they both have a right angle. And they share angle C. Alright, so I've proven those two triangles to be similar. Now let's do triangle ABC and triangle ADB. Alright, so once again, I know they both have a right angle, so there's one angle that's equal. And also look at my name. They both share angle A. So once again, triangles ABC and ADB are similar by the angle-angle criterion. I forgot my eye up here. Because they both have a right angle. And they share angle A. Alright, so they are similar by the angle-angle criterion. Is triangle ABC similar to triangle DBC? Well, let's look at this. Let's go back and look. Is triangle ABC similar to triangle DBC? Now here's where you have to be very, very careful because of the way they are named. Alright, so I'm looking at this small triangle versus the whole triangle. ABC. Angle B is my right angle in this triangle. But angle D is the right angle in this triangle. When they named them, did they match them? No, they did not. Their corresponding angles do not have equal measures. So angle B and angle D do have equal measures, but angle B is the middle one here and angle D is the first one here. So because of the way they wrote their names, these are not similar triangles. So triangles ABC and DBC are not similar because their corresponding angles do not have equal measures. Alright? So because of them mixing their letters up, the two triangles they're asking about do not meet the criteria of being similar. Since triangle ABC and triangle BDC and triangle ABC is similar to triangle ADB, can we conclude that triangle BDC is similar to triangle ADB? Explain. Alright. This one is similar to this one. This one is similar to this one. You notice they are both similar to the same triangle. So the transitive property can be used in similarity. Alright? So similarity is transitive. So since they're both similar to since they're both similar to the same triangle, then I can say that those two triangles are similar. So triangle BDC is similar to triangle ADB since they are similar to the same triangle. Okay? Alright, identify the altitude drawn in triangle EFG. Well, my altitude is GH. Alright? As before, the altitude divides the triangle into three triangles. Identify them by name so that the corresponding angles match up. Alright, so let's go ahead and start with our big one. So I have triangle EFG. Notice I put my right angle at the end, and that's okay. So then let's go to this one right here. So we'll go triangle EGH. I want my right angle at the end. Alright, and then let's go here. So I'm going to do triangle GFH. My right angles are at the end of my names. Okay? And guys, you can name them differently but you have to make sure the corresponding parts match up. Does the altitude divide triangle EFG into 3 similar subtriangles as the altitude did with triangle ABC? Alright, so we have to figure this out. Alright. Since we don't have I'm not going to waste a whole lot of time here. Since I know that these two triangles are similar, and these two triangles are similar, then what you're going to know is that these triangles are similar. So yes, triangle EFG is similar to triangle EGH, which is similar to triangle GFH. Alright? And that is by the angle criterion. Once again, I can see that these two triangles share an angle. They share angle E, and then our right angle. These two triangles, let's go to these two triangles, share a right angle and angle F. So therefore that makes them similar. So since they're both similar to the big triangle, then we can say they're all 3 similar. The fact that the altitude drawn from the right angle of a right triangle divides the triangle into 2 similar subtriangles, which are also similar to the original triangle, allows us to determine the unknown lengths of right triangles. Alright. So it says consider the right triangle, triangle ABC below. Alright. Draw the altitude BD from vertex B to the line containing AC. So we have to draw our altitude. It is not going to be perfect. It's okay. And that is altitude BD, so we're going to name that point D. And it says, label the segment AD as X, the segment DC as Y, and segment BD as Z. Okay? Now, here's what you got to remember. AC is equal to 13. That whole thing is 13. Alright? Find the values of X, Y, and Z. Alright, so we can look at this and find our values of X, Y, and Z. Alright? I'm going to show you really quickly. We're going to kind of look at a strategy for determining the lengths of X, Y, and Z. It says the strategy requires that we complete a table of ratios that compares different parts of each triangle. Alright? Make a table of ratios for each triangle that relates the sides listed in the column headers. So triangle ABC, the shorter leg to the hypotenuse. Alright? Well, so triangle ABC, the shorter leg is 5, and the hypotenuse is 13. Alright? Same triangle, the longer leg, which is 12, to the hypotenuse, which is 13. And then the shorter leg, which we said was 5, to the longer leg, which is 5 to 13. I'm sorry, 5 to 12. Alright, let's look at triangle ABD. Alright, so ABD, my right angle is D, which means my hypotenuse is 5. My shorter leg is X, so we're going to say X to 5. Alright, my longer leg is Z, and we said the hypotenuse was 5. And then my shorter leg X to my longer leg Z. All right, now we're going to look at triangle CBD, or CDD, sorry. So my shorter leg, which is Z, to my hypotenuse, which is 12. My longer leg, which is Y, to my hypotenuse, which is 12. So then my shorter leg Z to my longer leg Y. Alright, so we should have that filled out. Our work in example 1 showed us that triangle ABC is similar to triangle ADB is similar to triangle CDB. Since the triangles are similar, the ratios of their corresponding sides will be equal. For example, we can find the length of X by equating the values of the shorter leg to the hypotenuse ratios of triangles ABC and ADB. Alright, so X over 5 is equal to 5 to 13. And then I would treat this just like a ratio, a proportion, cross multiply, and then solve. Why can we use those ratios to determine the length of X? Well, we can use those ratios because the triangles are similar. Alright, we can use them because the triangles are similar. Similar triangles have ratios of corresponding sides that are equal. Alright, what ratios can we use to determine the length of Y? Well, let's go back and look at this. So we want to figure out the length of Y. So I can use my Y over 12 and my 12 to 13. So I can use, since those two triangles are similar, I can use that as my ratio. So we can do Y over 12 is equal to 12 over 13. And we're going to solve this. So I get 13Y is equal to 144. Divide by 13. So Y is going to be equal to, what, 11, so that'd be, and then 1/13. Okay. Use ratios to determine the length of Z. Alright, so let's go ahead and look at the length of Z. You can do this several different ways. We're just going to look at one way. So to determine the length of Z, we can use our Z to 5 here is equal to 12 to 13. I can use Z to 12 is equal to 5 to 13. I can do, I figured out what Y is, so I can use that. I figured out what X is, so I can use that. We're just going to do one that's simple. So we'll do Z to 5 is equal to 12 over 13. Alright, so I get 13Z is equal to 60. So divide. So 13 goes into 60 approximately 4 times. So that would be 52. So I have 8 over 13 left. Since corresponding ratios within similar triangles are equal, we can solve for any unknown side length by equating the values of the corresponding ratios. In the coming lessons, we will learn about more useful ratios for determining unknown side lengths of right triangles. Alright guys, so that is the end of lesson 21. Have a great day.